In this lesson, the first thing we'll do is do a quick review of what we learned last week and how we can extend on that. So the example I'm going to start with is, suppose I want to find the derivative of f of x equals negative 3x squared, x negative 3x squared plus 2 at the point where x is equal to 1. And before I do this example, notice that's just a parabola. So we've got the graph here, and remember, finding the derivative at x equals 1 is the same as finding the instantaneous rate of change, or the slope of the tangent, at the point, and it's actually 1, negative 1 is the point here. Okay, and of course if you sub in x equals 1 into this equation, you will get negative 1. So I can clearly see that's going to be a negative answer, definitely going to be larger than negative 1. So then we start with the definition of the derivative. Okay, the limit as h approaches 0 of, in this case, f of 1 plus h minus f of 1 all over h. Okay, again, just getting that from the slope formula. We want the smallest run we can possibly have. Okay, so I plug in my formula, noting that f of 1 is equal to negative 1. Okay, so there's the negative 1 right there for f of 1. Okay, and then for the equation, negative 3x squared plus 2, when I plug in 1 plus h, I have to square 1 plus h. Okay, and then multiply by negative 3, add 2. And then it's just a matter of simplifying this and seeing what happens. Okay, if I expand 1 plus h squared, I get h squared plus 2h plus 1. Okay, plus 2, and then of course subtracting negative 1 is just adding 1. Okay, I'm going to multiply everything here by negative 3. Okay, collect all my like terms and all that kind of stuff. And I end up getting the limit as h approaches 0 of negative 3h squared minus 6h all divided by h. And of course something nice happens here because I can divide by h, which just gives me the limit as h approaches 0 of negative 3h minus 6. And now this is no longer an indeterminate limit right here. So I can drop the limit as h approaches 0 by just subbing in h equals 0. And I get negative 6. So sure enough, this instantaneous rate of change here is equal to negative 6. So now imagine that you wanted to do that again, but you wanted to know the instantaneous rate of change at other points on the graph besides x equals 1. So, maybe at x equals 2, 3, or 4, and so on. You can see that this would take a lot of work and it'd be pretty repetitive. So if I started doing it for x equals 2, I'd have to do all this work again. But I'd have to plug in x equals 2 instead of 1, so here and here. Okay, I then have to figure out what f of 2 was, and I would go through and do this work, and I would actually find the same kind of things end up happening. That I always expand, divide out an h, and get an answer. Now, it wouldn't be negative 6 every time. Of course, it would be different numbers depending on what point you're working with. This would feel pretty repetitive. It's probably already feeling kind of repetitive as you did some of these questions last week. You find something like a quadratic always kind of works out the same. So we're not going to do that. Okay, there's something else we can do besides just redoing this every single time we want the derivative at another point. Instead, we're going to come up with a derivative function. So why not just, when we did this work, why put a 1 here? Why not just put an x and figure out what the derivative is in terms of x, and then you would actually be able to plug in x at the very end for whatever you want. I'll try to explain that a little bit better. Now, the first thing I'm going to tell you here, right here, is this notation right here, okay? That f and the little apostrophe a, that's actually pronounced f prime of a. But don't worry about that yet. We haven't actually talked about what that means yet. Okay, I'm going to explain that at the end. Maybe I should have taken it out of this example, but I'll leave it in for now, and at the end we'll explain what this notation here and what this notation here means, so don't worry about that quite yet. More importantly, to figure out the derivative, we do this calculation right here, okay? And we plug in our a value. In the first example, it was 1. I just picked 1 at random. But like I said, imagine instead of putting a 1 in here, we left it just with x. And then we did all the work without actually putting in x equals 1. And we saved that until the very end. Well, let's try it. What will we get? Okay, so how would we find, let's call finding, we just call this finding the derivative, by the way. So rather than worrying about what happens at x equals 1, let's just leave it like this and see what happens. Okay, so we have the limit as h approaches 0 of f of x plus h minus f of x all over h, but here's our f of x. So now we're going to say -3. Okay, instead of squaring x, I'm going to square x plus h. Okay, plus 2. Subtract f of x, which is just -3x squared plus 2, and I need that in brackets. All over h. So notice what I've done here is this is very similar to what we did in the other example, only I have taken, instead of having a, oops, sorry about that. Instead of having the 1 here, I've left it as x. So here, instead of 1 plus h squared, we have x plus h squared. Instead, in here, instead of actually getting a number, like if you plug in 1 here, you get -1 for an answer. I just have this expression here. And let's see what how the math works out when we do that. So limit as h approaches 0. Okay, if I expand, so the first thing I'm going to do, I'm going to expand x plus h squared. Okay, I do that, and of course I get x squared plus 2xh plus h squared, just multiplying x plus h plus x plus h. I also took this negative and distributed over the bracket, so I get positive 3x squared and minus 2. And now what we're going to do is we're just going to clean all this up. So we're going to multiply everything in here by -3. Notice the 2 and the -2 will disappear. Let's see what the next line looks like. Okay, and there we have it. Now notice that not only did the 2 and the -2 subtract out, but also the -3x squared and the positive 3x squared are going to subtract out as well. And we'll get the limit as h approaches 0 of, let's see, we'll have -6xh minus 3h squared, all divided by h. And that's very convenient, of course, because the h will divide out. Yeah, and I get -6x minus 3h, which is no longer indeterminate. For example, I mean, that's always a good thing to check, by the way. Notice that up here, if I subbed in h equals 0, I get -3x squared plus 2 minus -3x squared plus 2, which is 0 divided by 0. So it is an indeterminate limit, which it should be. And then down here, subbing in h equals 0 just gives you -6x. So what we have basically, I mean, this result's really important. This is what's called the derivative function. So at any point in time on the graph of -3x squared plus 2, the rate of change will always be equal to, -6x. So if we wanted to know the rate of change when x equals 1, sure enough, we got the slope of the tangent, or the instantaneous rate of change, is equal to -6 when you plug in x equals 1. Well, if you wanted to know what it was at x equals 2, you just sub in x equals 2, and you get the slope of the tangent is -12. Okay, and if you wanted to know what it was at x equals 0, you could just plug in x equals 0, and that's pretty easy to see that at x equals 0, you're going to get 0. And I think that's a pretty important one to realize, that you can actually see that on the graph, because sure enough, if I look at the graph right here at x equals 0, the tangent line is just a horizontal line. Okay, so it has a slope equal to 0 at that point right there. So there it is. There's the derivative function. So why bother doing this? I mean, why sub in x equals 1 at the beginning here? Why not just leave this as x? And at the end, you can sub in x equals 1. Because you can see this limit here wasn't really any easier than this one with the x in it. Okay? So really, after seeing this example, you probably won't ever do this again. Okay? And actually, what's interesting is as this course goes on, you're going to find out that we're going to learn some stuff that's going to make it that you don't actually do any of this stuff again. But for now, you do need to know how to do it. So let's talk notation now. Notation's important. You know, there was this f prime of x I was talking about, and I didn't really explain what that meant or anything like that, or f prime of a. So let's talk calculus notation. Basically, the idea is, look, I mean, this is nasty to write this over and over and over again. Okay, so there's language that we use for this kind of stuff. I've already introduced the idea of a derivative. The derivative, there's two ways you can talk about a derivative. A derivative at a specific point is the instantaneous rate of change of the function at that point, or the derivative function is a function that describes the rate of change of all the x values. For example, in the example we did here, this negative 6x, this is a function. This is a function that gives you the rate of change of f of x. So we actually describe that as being f prime of x. So in the other example, we have, f of x is equal to, it was 3x squared minus 2, and then we call the derivative function f prime of x, which was, it was negative 3x squared plus 2, which was negative 6x. So these two functions kind of have a nice relationship. F of x is like the original function, and then f prime of x is the function that describes the rate of change of f of x. So you can use f prime of x to calculate the derivative of any function, any part of f of x, okay? Now, that also means that you can talk about f prime of, for example, 1, which would then be negative 6. So just like you can talk about f of 1 with function notation, you can talk about the derivative at x equals 1. So really, in this other example, the very, very first example, we actually found this right here, find the derivative of f of x at x equals 1, is the same as just saying, if f of x equals this, then just find f prime of 1, which is exactly what we found. So that was what I did right here. I mean, this right here, I could say, therefore, f prime of 1 is equal to negative 6. The derivative of f of x at x equals 1 is negative 6. And then over here, I actually just found f prime of x. So not for any specific number, but for any x value. And then, of course, over here, there's f prime of 2. I mean, I'll just do one of these here, but this right here tells you that f prime of 2 must be equal to negative 12. The instantaneous rate of change at x equals 2 is negative 12, or the derivative of x equals 2 is negative 12. Okay, so a little bit more about notation. There's actually two different notations that we use in calculus. And here's what happened. Isaac Newton and Leibniz, who's German, discovered calculus basically at the same time in the late 17th century. So calculus is, in the spectrum of all the math that you learn in high school, calculus is actually some of the more modern math, if you can believe that. Late 17th century isn't that long ago compared to some of the other things that you do in math, which have been around for a really long time. I'm not actually sure about when the vector stuff would have been discovered, but I could look into that sometime. In any case, they both had their own notation, and they're both still useful depending on the circumstances. So in most branches of mathematics, one notation has kind of taken over as the accepted notation. But with calculus, there are actually both of these notations, and they're both useful, and so they both have stuck around. Okay. The first one, the one I've already sort of walked you through, is it's either called prime notation or Newton notation, because it is Isaac Newton's notation. You refer to the derivative of f of x as f prime of x, and then of course the derivative at different x values could be f prime of negative 1, f prime of 2, f prime of 3, and so on. For most of the work we've done so far, prime notation makes more sense. It's easier to work with. In fact, even the definition of the derivative here kind of implies that you're working with prime notation. I'll explain that in just a minute. Leibniz notation, he refers to the derivative as, see this little fraction here? dy by dx. That's how you say that, dy by dx. So if y equals negative 3x squared plus 2, then we'd say dy by dx is equal to negative 6x. Okay, that's the notation. Now it's slightly more difficult to talk about the derivative of x equals 1, x equals 2, and so on. I mean, there's a couple ways to do it. So if we want to know, say, the derivative at x equals 1, then one way to do it is you could just use the words at x equals 1 dy by dx is equal to -6. That's one way to do it. It's kind of like, notice here, you're not dealing with function notation. So it kind of has the same problems. As soon as you're not dealing with function notation, you can't say f of 1, f of 2, and so on. And so it's the exact same kind of thing happens when you're dealing with a derivative. There is one other way to say this that is sometimes used. They sometimes say dy by dx. They draw a little bar and then say x equals 1. Oops, sorry, there should be no highlighter there. X equals 1, and then they say equals -6. We'll see that from time to time. It's not exactly how it works, but it's kind of like that. So you can do that too. You can even combine notations. So this idea of dy by dx is basically saying, look, take the derivative of y with respect to x. So basically evaluate the rate of change of y. How does it change as x changes? Okay, so it kind of becomes like an operator. This d by dx is kind of like a derivative operator. So one thing you can do is you can do, you could say you had r equals s squared, for example. You don't use y and x, you don't have to. You can say dr by ds. In this case, you'd find out you actually get 2s. Okay, why? I just happen to know the shortcut for that one. So there's another way you can use it. It can be different variable names. Sometimes you might have a function with 3 variables in it, and you might take the derivative with respect to just one of them. And Leibniz notation is the only really good way to do that. Prime notation doesn't have a good way of doing that. Rather than saying here, instead of saying, if y equals -3x squared plus 2, then dy by dx equals -6x, you could just do this. You could say, I could take the derivative of -3x squared plus 2 with respect to x. So I'm basically saying, instead of the derivative of y, the derivative of this stuff with respect to x. And then, of course, that would be, it's the exact same thing. It's still -6x. So there's another way to do it. And that's kind of what's going on down here. The derivative of f of x is equal to f prime of x. So if you only knew Leibniz notation, you could introduce prime notation by doing this, saying the derivative of f of x is equal to f prime of x. And now I've introduced prime notation. So at first, you're probably not going to like this notation as much. It's going to seem like more writing. For now, you really just need to be comfortable with what this idea of dy by dx means. And later on in the course, you'll see there's just some cases where it's just so much easier to use Leibniz notation. And there are certain things you can really only do with using Leibniz notation. So nobody gets away with just using one of the notations. Another thing about dy by dx, it's not a fraction. I know it kind of looks like one, but it is not. It's just it's a notation. So the last little note I have here is, like I said, you're going to find that this notation is less useful. Right now, that will change. For now, you should use Leibniz notation if you're given a function written in form y equals. Okay, if it doesn't use function notation, use Leibniz notation. And if it does use function notation, then go with the Newton or the prime notation. Like I said, they kind of discovered calculus at the same time and actually did argue over who deserved credit for it. So kind of an interesting little history story there too. Okay, so let's look at an example now. Find the derivative of y equals 3 over x squared minus 1. So finding the derivative is the same as asking you to find dy by dx. That's exactly what they could have just said find dy by dx. Sometimes you might just say differentiate this function as well, meaning find its derivative. Okay, there's the graph right here, okay, of y equals 3 divided by x squared minus 1, couple vertical asymptotes at x equals 1 and -1. Okay, so dy by dx equals, we can set up the definition of the derivative. The limit as h approaches 0 of f of x plus h, f of x plus h, minus f of x, all divided by h. Now, there's a little bit of a problem here. There's no f of x, right? This is y equals. So we decided to do Leibniz notation because we had y equals, but then the definition of the derivative uses f of x. It's not a big deal. One thing you could do is you could write let y equal f of x so that you can use f of x. The other thing you could do is you could skip this. Oops, sorry. You could actually just skip this line and go right into the fact that dy by dx equals the limit as h approaches 0 of 3 And I'm actually going to I could just skip and go straight into the work. X squared is now x plus h squared. Take away 1, minus 3 over x squared minus 1. All of that is divided by h. So you could skip this idea, or you can include it. It's not uncommon to see it. Everybody kind of gets the problem with Leibniz notation is how do you do the definition of the derivative. Sometimes you'll see dy by dx is just equal to the limit as delta x approaches 0 of delta y over delta of x. So that's another common, like Leibniz might have said this was the definition of the derivative if he wasn't going to use f of x, okay? So the limit rise of a run, but the limit as the run approaches 0. So there's another way to do it. In any case, this is the important line right here, okay, where we have this set up. Unlike before, we're not subbing in a value for x, we're just finding it for every single value of x. So lots to do here. We got some simplifying we need to do to start. Okay, now we got a choice. We could expand all of this, okay? Eventually, we're going to put these two fractions together. I'm tempted to say, let's put the two, there's no right or wrong answer here, but I'm going to put these two fractions together with a common denominator and then worry about what that denominator looks like at the end. So that means I'm going to have 3 times x squared minus 1, subtract 3 times all of this stuff here, x plus h squared, take away 1. Okay, all of that is over my new common denominator, which I get from multiplying these two together. I know the algebra is a little bit nasty. Okay, that's what happens with calculus. Okay, so here what I've done is I found a common denominator for the numerator of the big fraction, okay, by multiplying each fraction by the other's denominator, and then of course the common denominator is just these two multiplied together. And all of that is divided by h. Well, if all of that is divided by h, that means I'm going to multiply by 1 over h. Let's do that right now, or this just gets so messy so quick, okay? From there, we're going to expand, certainly on the top. And I'm tempted to say that maybe I'm going to leave this alone because maybe it won't matter. Like maybe I don't need to expand that to figure this one out. So I get 3x squared, take away 3, subtract 3 times, and I'm going to figure out all this stuff here. I get x squared, x plus h times x plus h is x squared plus 2xh, okay, plus h squared minus 1, just like that. And then all of that is over, I've got my h here still, I'm going to just write it out front. And then I've got my x plus h squared, take away 1, and that actually needs to be in brackets again, times x squared minus 1. Okay. All right, so now I'm just going to expand everything here and collect like terms, and I'll do that and see what we get. Okay, and there you see it. So I multiplied everything here by -3. Now what is going to happen next? Notice that the 3x squared and the 3, oh, I've made a little bit of mistake here. Let me just fix it. There, that looks better. So I've got my 3x squared minus 3. I multiplied everything here by -3. There's some stuff that's going to subtract out. The 3x squared and the -3x squared will subtract out. So I can just kind of stroke those out here like that. And like that, okay. Oh, there's a +3 and a -3, okay. And so I get all this stuff right here. Sorry, just ignore that for now, it's in the way. And there's what you get when you clean all that stuff up. And then this is an important step because sure enough, we notice that everything I can divide out in h. So divide an h off the bottom and top of this, and then I get rid of this h, and I get rid of one of the h's. Just going to do that now, okay, so I get the limit as h approaches 0 of -6x minus 3h, all divided by x plus h squared, take away 1, divided by x squared minus 1. So that denominator is a real mess there, But as it turns out, as soon as I divided this by h, that's when the limit is no longer indeterminate. So I can actually sub in h equals 0 now. Notice I couldn't do that here because it had 0 on the top and 0 on the bottom, 0, 0. But now I can, and I just get, okay, so negative 6x in the numerator. And in the denominator, I plug in h equals 0. I'm going to get x, so that's going to give you just x squared minus 1 times another x squared minus 1. And there you go, which can also be written as negative 6x over x squared minus 1 all squared. And there's our derivative, dy by dx is equal to negative 6x over x squared, take away 1, all squared. That means that I can then use this function to determine the rate of change at any point on this curve that I want to. Okay, so for example, at x equals 2, plug in x equals 2, and you're going to get, what, negative 12 over, I don't know, 2 squared is 4 minus 1 over 9, so negative 12 over 9, which is negative 4/3, sounds about right. Ooh, notice that x equals 0 here. See that there's a horizontal tangent line right here? Horizontal tangent lines are pretty important. You can probably guess why. Usually turning points. But here's the horizontal tangent line. And sure enough, if I plug in x equals 0 into this equation right here, I will get 0 divided by 1, which is 0. So that makes sense too. Notice that this worked out nicely. All the stuff canceled out that needed to so that I could divide by h and no longer have an indeterminate limit. That will always happen. If that doesn't happen, it means something's wrong. And the reason it always happens is the derivative function exists and it can be found this way. Okay? If you were to change, say, the 3 to a 2, well, then you would notice that it's 2x squareds that end up canceling out and so on, and you just get a different answer, but you would still get one. Okay, so there it is. There's differentiation. Now, this process, by the way, is called using first principles. Using first principles implies that you're using limits to calculate derivatives. There are other ways to calculate derivatives. I mean, we did just kind of guessing and checking with a table, but first principles means no shortcuts. There are shortcuts coming up. So by the time you finish calculus, you will know how to find the derivative of this function here without needing to use a limit. You'll know the rules. It's actually not a super easy one. There's quite a bit. We're not quite close to doing that yet, but we will get to it. But this whole process is called using first principles. But right now, that should be the only way that you know how to calculate a derivative is using first principles, using limits. And I definitely encourage you to practice some of those for your work that goes with this lesson. Okay, that's the end of this.